Hi there, this is Jacob Nash, and in this video we'll be looking at trig integrals. Well, first of all, I want to start by saying that this isn't the same as trig substitution. That's what we'll be going over in the next video. And if you're going to do trig substitution, that's where you see something like maybe a square root in a denominator. But this is something different where we just see trig functions to start with. Trig substitution is when you plug in a trig function and the starting problem will have that in it. So if you don't even know what that is, then don't even worry about it. That will be in the next video. Sorry. So what ways do we know how to integrate so far? We know the normal way, right? Like just using our reverse power rule or whatever freaking thing we've already known. Then the second thing is U sub, which hopefully by now is pretty easy. And then also in the last video, we looked at integration by parts, which is a little harder because it just takes more time, but also isn't so bad. But this one that we're going to learn in this video probably is harder than the ones that I just mentioned. Mostly because you really have to do a lot of outside thinking. The other three, it's a pretty simple process that you can learn, like first do this, then do this. But for these problems, they're never they mostly can fall into three categories of types of problems, but that you also have to do a lot of outside thinking to figure out what to do, unfortunately. But how you know that you're going to do a trig integral is that you'll just see a trig integral that you don't know how to do. So you'll see something like tangent to the fourth. I don't know what that is. I don't know what the integral of that is. Or sine squared times cosine cubed. I don't know what that is. Almost every time there's something multiplied like that, you don't know what to do. But remember, never make things harder than they need to be. There are some trig integrals that we do know how to do just simply by the fact that doing the antiderivative is the opposite of when we do the derivative, which remember, fundamental theorem of calculus you might have learned before. So let's look at these and hopefully we know some of these, right? All right, what's the integral of sine? Negative cosine, and you might be thinking, why negative? Well, cosine itself will only give you, when you take the derivative of it, it will give you negative sign. So if we start with negative sign, we'll have to, the derivative of negative cosine is what would give us sine. Because if you remember, any trig that starts with a letter C, if you take the derivative of it, it's negative. Like cosine, cotangent, cosecant. They always end up with negative derivatives. So the reverse is true. So sine positive, you when you do the integral, it's negative cosine. Now if you do the derivative of cosine, sorry, antiderivative integral, what the heck? Sorry, I guess I copied and pasted that, forgot to change it. But the answer will be sine, positive sine, because positive sine gives us positive cosine. So sorry about that. I must have just been stupid and not changed it. All right. Okay. Oh yeah, yeah. Or yeah, we have secant squared, right? Oh no. Nope. So sorry. That's a common mistake that someone would make. If you do the integral of um tangent, that does not give you secant squared. That's if you do the derivative tangent. So really don't mix these up. They're easy to get confused, but actually we don't even know that. That's not something that we can just know, like that's the purpose of this video. And yeah, yeah. Same thing for those. We don't actually know those. Um because remember there's no derivative that we know that will give us those. Now, secant squared, we can do that. That's what tangent is. That's what you might have been thinking of. It's reverse. And then this one's just going to be cosecant, right? uh, Cotangent. So just don't get mixed up. Don't flip these around. Remember which are derivatives and which are integrals. And then this one here, I put this one here for a reason because you might be like, what the heck? What is that? Like, why is the dx over there? They'll do that sometimes to confuse you, but really what this just means is 1 over 1 plus x squared dx. That's the same thing. And that's arctangent. So don't forget about the arc whatevers. And it's a good idea to remember all of them, but I think this one in particular will be really important to know, the arctangent for this course. So don't forget that. So anyways, what do we do for the ones that we don't know? What do we do for those? we'll have to use trig identities to make these work. We'll just have, that's what the theme is for calculus so far, right? If something is stupid and we don't know what to do with it, change it so that it is something that you can do. That's pretty much what you always have to do. Um, so if we don't like what something looks like tangent to the fourth, I hate that freaking thing, change it with the trig identity to make that something that you do know how to do. So here's one trig identity we hopefully know. Cosine squared x plus sine squared x equals 1. That is something that you just have to memorize if you haven't already, but not that hard to remember, right? And then there are other ones that you want to memorize, but it's kind of easy to memorize it. So if we decided to divide all those things by cosine squared x, what is cosine squared divided by cosine squared? That's just 1. What's sine squared divided by cosine squared? Remember my thing, if you've watched my other videos, I say t equals s divided by c. Tisk. I hate trig. Tisk. That's what I always remember. So s divided by c equals t. T equals s divided by c. Tisk. So that's going to equal tangent, and then 1 over cosine, that means it's just the reverse or whatever you call it, inverse. So secant squared. So this is another trig identity that you would want to memorize, but if you also just feel like not memorizing it, you can just remember divide by cosine. You can also divide by sine squared, and we're going to talk about that later in the video, but that's another one. Now, this is one that you might not know. This is what's called the double angle identities. You don't really have to know the specifics of this, like you don't have to know how we derive this necessarily, but you will have to use these and you will have to memorize them. So if you notice, they're the exact same. One has a minus, one has a plus, but these are equivalent to sine squared and cosine squared respectively. So you will want to memorize that definitely. And I'll tell you how you know which to use. So here are the steps for these types of integrals. First, there are 3 different categories, as I mentioned, that this might fall into. The first, so the first is if we have 2 trig functions that are multiplied by each other, and the exponents of them are either both odd or only one of them is odd. That is the first case. The second one is that they're both even exponents. The third is that there's not actually 2 trig functions multiplied by each other. There's only one. Those are the only 3 possibilities that we'll go over at least. Um, this after you've identified which one of those it is, split the odd one or the bigger one, and that really only is applicable to cases number 1 and 3. We'll look at this though. But if you see something like cosine to the 5th, if that happens to be the odd one, the only odd one, or the bigger odd one, then you split it like this. You just have one by itself, so just cosine x, and then we would have what's left, cosine to the 4th x. So that's equivalent, right? Because if you multiply those, you add the exponents. After that, you use a trig identity. Some people might skip to u sub, and then you'll end up getting the wrong answer, so don't forget about this. Use the trig identity that we had on the last slide, and whichever you use will end up needing, and that says 2 identities. I'm sorry, it's supposed to be 2 functions. Okay, sorry about that. Yeah, I fixed that right there. It's supposed to be 2 trig functions, not trig. Yeah, 2 trig functions so that the u sub will work because that's what you'll do next, and then integrate like normal. So let's look at an example. So if you see here, we're integrating cosine squared x times sine cubed x. How do we know we need to do trig sub? Well, we don't know any other way. All the other ways we know do not work for this. So that we obviously will have to do that. If you see 2 trig functions multiplied by each other, you'll usually have to do this. So the first thing that you do is, which case is it? Are they both even, both odd? One is odd, or only one function? Obviously, one is odd. If one is odd or both are odd, you do the same thing. But in this case, there's just one odd. And what you do is you split the one that's um odd, like I said. So look what we do here. We put one sign by itself. That's what you always do. You have one by itself and then what's left right beside it. So this is equivalent to sine cubed, right? Sine squared times sine x. and then we still have the cosine x here. Then what you do next is you replace um, one of the ones that there are two of with a trig identity. So what is there two of? The sine x's. So you replace it with the trig identity. What is sine x? Sine, and this is the one we'll have to use because there is no trig identity that applies to sine x, only sine squared x. So using this trig identity that you need to memorize, solve for sine squared x, it equals 1 minus cosine squared x. So we plug that in there. That's the next step. So like I said, first you split it. Second, you plug in a trig identity. Now we do u sub. Now how do we know which to set u to? Here's a tip. U will never be something squared or something cubed or whatever. It's always just going to be something with to the first power. That's always how it will be. So the only two options are ever going to be the two functions that you see. It could only be cosine x or sine x. Those are the only possibilities we could choose for u. How do we know which one? It will always be the one that you see two of. So I see two cosines. That's what u will be. That's how it goes. Like I said, also for when you plug in a trig identity and trig identity, sorry. Always what you choose for plugging in a trig identity and what you choose for u is what you see two of. The reason why is that if you chose what there's only one of, then you would end up with all the same function and then you couldn't do anything. So we will set u to be cosine x. The derivative of cosine x is negative sine x. And so then dx is going to be du divided by negative sine x. So in that case, the sine x is canceled out, right? Hopefully this is just review of u sub. And then the negative, don't forget the negative, it's right here. It ends up right here. And we replace all the cosines with u's. So u squared times 1 minus u squared. You 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 multiply that in, sorry. And the order just got switched, but it's just u to the fourth minus u to the second, and then power rule, as we know, you just add one to the exponent and do what we already know, and then you replace it with cosine at the end, and don't forget your plus c. Bingo. That's not so bad, right? But just you, and I have this purple box over here. These are the only four identities that you'll use, and it's based on what's in the problem, so it's obvious that what one we would use is the one that has cosine and sine in it. So just to review what we did in this example, we first split the one that was odd, and then we replaced what there is two of with the trig identity. Then we set u equal to what there is two of, and then we did u sub, then we did our normal things that we already know. Here's another example that's just like that one, just for some repetition, I guess. Which one is odd? The cosine. Bingo. You split that apart. Um, ooh, actually, this one's a little different. So this one's a little different. So if we do what I said for you to do before, we would have cosine x times cosine to the fourth. Because remember, you split it to where there's one by itself and then the rest. But the reason why I did cosine squared is because the identities that we know only have cosine squared in it. So cosine to the fourth won't do us any good. So we split it apart like that. And we have a sine squared here. And then you substitute what there is two of. And actually, I really shouldn't say two of, I guess more than one of. And that happens to be cosine squared. So we replace it with, if we use a trig identity and solve for cosine squared x, it equals 1 minus sine squared x. So you plug that in here. And why is it squared? Because there were two cosine squared. Cosine squared. Don't even know how to say that really. So there you go. Now you set u to equal what there's two of. What is there two of? Two sines. U equals sine x, du equals cosine x, dx equals du over cosine x. So the cosine x's go away. That's always what's going to happen in the u sub. One of the trigs will go away by to the stupid thing. By cosine x, so it gets canceled out. If it doesn't cancel out, you obviously did something wrong. Because, yeah, u sub only works if one of the functions cancel out. Now we just replace the signs with u's. bring that exponent in, and then we go down here. This is what we would end up. You have to also multiply by that in there. And then normal thing that we always do. I'm not even going to go through that because that's in a previous video. Hopefully by now this is second nature for you to just add one to the exponents and make sure the fractions are right on the side that it would multiply back if you did the derivative. Okay. Okay. Now, as I mentioned, sometimes what I just showed in these last two slides, they would also work if both of them were odd. It works if one is odd and it works if both are odd. But what if they're both even? Then instead, we can't use any of these four right here. We have to use the double angle identity. Some people also call it the half angle identity, so whichever you prefer. And that happens to be this right here that you'll just have to memorize. So what do we see this thing? We're like, that's stupid. So let's replace it with these. So what do we have here? We just go bingo, bingo. We plug those two in. Now you would um we end up actually being able to take a 1/4 out because we have a 1/2 here and a 1/2 here. So that goes out, and then you multiply these using the FOIL method. So 1 times 1 is 1. Positive cosine 2x times, or sorry, plus, uh, you know how to do that. I'm not gonna, it's hard for me to vi verbally say how it is, but it would end up like this. Anytime you have a minus and a plus and it's the same thing, you end up with only two terms, and it's 1 minus cosine squared 2x. Don't forget that it's 2x. Now, are we able to take the integral of this? No, we don't know how to do that. We do not know what cosine squared of 2x is. That's not something that we can do, but we can replace it with sine squared 2x because this identity actually still works just because it's a 2x, that doesn't matter. Um, so now we have this here, and now this, we actually, this is why this one's kind of hard. You actually have to revert back to, we still can't do the integral of this, which, sorry, the symbol, I don't know why it's not over here anymore, but that's supposed to be here and here. Um, we can't do that. We can only do something if it's to a first power and there's nothing else we can do. So we will go back over here and once again use this double angle identity. And why it's called double angle is it helps you know that when you go back, see how it already is 2x to start with over here, it's going to be 2 times 2. So that's how we end up with 4x right here. Because this is right here, but it's 2x instead of just x. So when you switch to the identity, you have to make it 4x. Now, we can do this. We can take out a 1/2 and then we have 1/8, um, which the way that this is solved is that then you distribute the 1/8, and so it's 1/8 minus 1/8 cosine 4x, and we can do the integral of that. It's just 1/8 x minus 1/32 sine 4x plus c. So that's a little bit hard. I feel like this is the harder one, but you just have, this is what I'm talking about like earlier in the video. Just this example like is not applicable to all. So you, depending on the example, you'll have to do different things. So the process that's in this example isn't going to be what you always do. It just happens to be what you do for this one. And I try to explain the best I could why you would do what you do. But the reason why we had to switch back to do the angle identity again is because we just don't know how to do this. This is nothing we can do. So we had to go back to this because I know that if it's cosine to the first, I can do the integral of that. So that's why we switched back again. Now, the case 3 is that there's only one thing. If you get an integral like this, well, that's only one thing. And I say thing, that's kind of vague. One trig function. And I can't do this. So what you have to do is, there's a lot of stuff right here, and I apologize for that. It's a little cluttered, but just skip down to here. You still break it apart, and you have to use an identity. Well, there's no identity that has tan to the fourth, but there is one that is tan to the second. Using this one right here, which is also right here, tan x plus 1 equals secant squared x. And in the beginning of the video, back on this slide, I explained how we get to that. So now we replace one of them with the identity, and so it's there. Well, now what? Um, well, we go over here, and you actually are going to distribute this. So tan squared x, secant squared x, and then it's split into two integrals to just make it a little simpler. Um, so that's what happened. That's what's going on in this red right here. Going from the green, we just distributed this. Now, we can actually do a U sub because we see this right here. That is something that can be canceled out. And it's actually kind of cut off, but we set D we set U to equal what there's two of. There's two tangent x's. But like I said, you never make it tangent squared x, so we just make it tangent x. And the derivative of tangent x is secant squared x. The reason why we're doing that is so that that stupid secant x squared will go away. But the u sub is actually only applying to this part right here, which is why we split it into two, which is once again tricky. But you just have to think outside the box. So that's why we split it, because the u sub is only going to apply for this. So um, u squared, all right, that's what we have here. And over here, you actually, once again, you can't do this. You cannot do the integral of tangent squared x. So we replace with the trig identity. Anytime that you can't do anything, you replace with the trig identity. And so that's what we do right here. We can do the integral of this, right? This is just tangent x. And then the 1 is just going to be x. And how it ended up positive is that negative right there distributes. And then here's just a power rule, and we get our answer. So that was a hard one. And, why is that you would have to just know, okay, going from here to here, you would have to distribute that tangent squared x and separate it. That's a little tricky. So sometimes it is trial and error. You might just have to try something. If it doesn't work, do something else. Case extra. Well, this is just a different thing, but this is a little bit different because they're both even, but since it's not sine and cosine, we can't use the double angle identity. So instead, we're just going to use the identity that has cosecant and cotangent, which is right here. 1 plus cotangent squared equals cosecant squared x. So we will replace um, one, we have this right here, and then we split the cosecant. There's really a step skipped right here, so I'll just write it. So we split the cosecant to the fourth into cosecant squared. That's what we did here. And so one of the cosecant squareds, we remember what there is two of, you replace with a trig identity. So there were two cosecant squareds. So we replace one with trig identity. Then you set u to equal what there's two of. There are two cotangents. Du equals negative cosecant x squared. And then dx equals du divided by negative cosecant x squared. So that's cosecant x squared's canceled out. And then you replace you replace cotangent with u. That's what we see. That's what we see. That's what we see. And then we do the normal thing. So that is it for this video. The truth is, I've mentioned already in the video that it is not possible for me to go over every possibility that you'll see. They're almost endless. Your professor could choose any exponents they want for the problem. And I'm just telling you, this is the way that you have to do it. To review, you know, if generally what you have to do is you have to split apart the exponents. Then you replace with the trig identity, and you replace what there is two of with the trig identity. Then after that, you replace what there is two of with u, and then the thing that you didn't choose as u will cancel out, and then you can go from there. So that's actually pretty much always what the process is, unless you use the double angle identity, which is only the case if you see two even exponents and its sine and cosine. Um, Everything else, you do what I just said. Um, However, it's not always that simple just because you have to take some steps to get to what you need to do. Sometimes you can't right away do a trig identity substitution or a U substitution. Sometimes you have to do some sneaky things like distributing or separating the integral like I showed. So the best thing that you can do is practice. Try to do as many practice problems as you can. This is definitely one of the trickier concepts. But I hope it helped. So thank you for watching.